Bon, ben, doucement dans la loi comme ça. Just give us 2 minutes. We are trying to solve some technical issues. We'll start very soon. It's better this way. Yeah, oh, yeah, definitely. I understand. About steerers. Okay, cool.
Hello, everyone. It's working, right? Hello, everyone. Welcome to our event. And I'm Mira Kharka. I'm one of the ECS volunteers. Okay. So let me introduce to our speaker today. She is Florence Collion. She is a representative of SCAR, which is Scientific Committee on Antarctic Research, and she is a paleoclimate modeler. And she will be talking today about West Antarctic ice sheet dynamics and why it is such a threat. Thank you. Welcome, Flo.
So I have to. Okay. That's okay this way? Okay. Well, thank you very much. That's a bit very fast preparation presentation to explain you a bit about West Antarctica, because half of the day will be also dedicated to East Antarctica with Chris talk. So we thought it was fair enough to also speak about West Antarctica. Okay, so Antarctica, it's a big ice sheet. Okay, geographically, it is cut in two main parts. Let's say by a big mountain range that are called the Transantarctic Mountains. Okay, they go from the Ross Sea sector, which is close in front of the New Zealand sector, and they just go across most of Antarctica up to the peninsula. Okay, so tectonically, those are two different plates. And they separate Antarctica into two main ice domes. Let's say there are plenty domes of Antarctica, but two main ice entity. East Antarctica, that contains most of the ice volume, that if would melt completely would rise global mean sea level by about 52 meters. And West Antarctica, okay, here on the left-hand part, that contains about 5 meters of sea level equivalent, okay, would rise sea level by 5 meters if it would melt completely. Antarctica is quite complex, okay, and I will explain everything in a moment. It has some sectors that are called what we call marine-based, okay, and as such, they are vulnerable to oceanic warming, and I will explain what that means. Actually, so the ice that accumulated on the continents, okay, is flowing because the ice is a medium that deforms under the action of gravity and temperature of the ice itself. So it flows toward the ocean, and when it arrives to the ocean, it starts floating. It creates some termination platform, That's floats that are about 400 to 200 meters thick at the front, okay? And those platforms are called ice shelf. So Antarctica is full of this marine termination of glaciers, much more than Greenland, for example, and most of them are much larger because Antarctica is much larger than Greenland also. So the particularity of Antarctica is to have most of the outlet glaciers floating on the ocean. So makes them, the floating part, very vulnerable to oceanic warming. Ice velocity is what really determines how fast ice discharge into the ocean and how fast Antarctica actually contributes to sea level rise. So if we look at satellite reconstructed velocity, um, in the interior, where you see the, let's say, orange color, the velocities of the ice flow are a few centimeters per year, okay? And while flowing to the margins, okay, with the slope of the ice sheet itself, and it arrives to the ocean. When arrives to the ocean, let's see if we can do that again. Yeah. When arriving to the ocean, okay, the ice velocity accelerates because there is no friction. I mean, on the continent, the ice is flowing on the bedrock. Okay, so it has a lot of friction at the base, and that's why the flow of ice is a few centimeters per year. So it's quite slow. If we stay on the ice sheet, we barely see it advancing. Okay, but when we arrive to the coast, okay, you see all those magenta colors. You see the streams lines here that shows that the ice flow is accelerating because of slopes, and also because when arriving to the ocean there is no friction anymore, it's water. So the velocity accelerates up to a few kilometers per year. Okay, so those areas are the areas where actually most of the ice discharge occur, okay, because those are the marine termination. Once the ice starts floating, after a while, let's say the fluxes of ice is not enough to maintain the platform forever, so they do not expand forever, and they calve, they form icebergs. Okay, that's how Antarctica lose the mass in terms of iceberg calving. When I say before, it's those platforms are very vulnerable to oceanic warming. It means that also ocean melts them from below, okay, because the ocean is much warmer than the ice. The ice is about minus 20 degrees. The ocean around is about minus 1 degree, minus 0.5 degrees. So it's much warmer. So the ocean melts the floating part of Antarctica, which here are shown by all those bright magenta and dark blue colors, actually. So I just evidence here the sectors that are marine based and most vulnerable to oceanic warming. So this is because if we remove the ice, okay, this is what is below Antarctica. So this is the subglacial bed on which Antarctica flows. And you can see that most of the bed below the ice, okay, is above sea level. Okay, those are all the brownish colors that you can see on the picture. But most of Antarctica bed is also below sea level. It has a topography that is below zero. What does that mean? Doesn't mean it just means that most of the ice is not floating. It's just anchored on a bed that is below sea level. Okay, and that makes the difference because, of course, if we are below sea level, we are much vulnerable to oceanic warming. And then, at some termination, we have those ice shelves, those floating platforms. What about oceanic circulation around Antarctica? I mean, this slide is important just to make you understand where the heat is coming from. So around Antarctica, we have a main current, okay, westward flowing current that is called the Antarctic Circumpolar Current, okay. This Antarctic polar circumpolar current is wind driven. Okay, so above the atmospheric circulation has strong westerlies that really makes the design the shape the current around Antarctica. The Antarctic circumpolar current has always been there since the Drake Passage opened between the Patagonia and the peninsula. So it's dated back 34 million years ago. Okay, that's when the passage really opened. So this is a very ancient current. It has always been there. And it isolates Antarctica from the rest of the oceanic basins in the surface, okay, because it's not a deep current. Then around Antarctica, most of the heat is then advected toward the coastline from this current, okay, which temperature is around 1 degree to -1 degree, okay, and most of the water is advected toward Antarctica because of existence of gyres, for example, like in the Ross Sea, which are regional currents that helps the heat transport and also transport the fresh water melt from Antarctica to the ACC and to the Southern Ocean. If we look at the oceanic temperature, so this figure shows you what is around Antarctica, the oceanic temperature of water around Antarctica, of this Antarctic circumpolar current. You can see that temperature varies from -1 to 1 degrees, and actually is especially warm along the coast of West Antarctica, okay, which is all this part here on the picture. You can also see that on Antarctica, the ice shelf, okay, so the floating part has been evidenced, and they show actually the loss of thickness of ice, okay, for those ice shelf. And you can see that in this sector, those ice shelf are very red, okay. All those parts here are red, so it means that they are losing mass a lot, okay, compared to all the other parts that are shown floating also, but losing mass, but much less, okay. And this is because in this sector of Antarctica, the Antarctic circumpolar currents and the warm water, that the subcurrent that transport the warmth, which is the circumpolar deep water, okay, transport the heat almost directly to the coast of Antarctica, okay, which makes all the ice shelf there particularly sensitive to the heat transport and the melt from the ocean warming. In other sectors, we have the heat has larger way, I mean, to go to reach the ice sheet because the continental platform is larger and the ice shelf are not directly exposed to the open ocean, so it makes them a little bit more protected from the rest of the ocean heat advection. Now, if we look at what the satellite shows us in terms of changes in elevation of the ice sheet, we can see that all this part of West Antarctica has been losing a lot of elevation, okay, means that it has been losing a lot of mass, a lot of ice, okay. Other sectors of Antarctica also show some ice loss, and some of them are the marine base sector of East Antarctica, which we'll be talking about this afternoon, actually. But you can see that West Antarctica is the main sector of Antarctica that lose the elevation right now because of this impact of ocean heat transport and ocean melting from below the ice shelf that are there. So that's quite striking. Now, if we combine all the numbers together and we make a sort of mean of mass loss around the different sectors of Antarctica, this graph shows you how much Antarctica, with the purple curve, has been contributing to sea level rise over since the 90s, actually. And you can see that most of this purple curve is mostly overimposed by the green curves, which is the contribution of West Antarctica. While you can see that East Antarctica has almost zero contributions, okay? And the Antarctic Peninsula has a contribution, but that cannot explain the trend of Antarctic mass loss, actually. So this is quite clear from this graph that most of the contribution of Antarctica to the 20th century and in the beginning of the 21st century is due to West Antarctic melting, okay? Why now do ice shelf are so important? Because most of the ice sheet community now is not only focusing on ice shelf, but mostly because, as I say, I mean, those are the marine termination of all glaciers, so the outlet where the ice discharge into the ocean. And we say at the beginning that because it starts flowing on the ocean, there is no friction at the base of the ice, so the velocities are a few kilometers per year, okay? And the role of this ice shelf anyway is to maintain most of the inland ice on the continents, okay? So they act as taps, like in bottle, for example. If we disintegrate those platforms, it's like removing a tap, and the discharge, the ice flow accelerates, and there is a huge discharge from the inland flow until the ice sheets in this sector reach a new equilibrium and stabilizes again, okay? And it forms a new tap, okay, a new ice shelf, until it disintegrates again and allow the flow to accelerate, increases the discharge and sea level rise contribution, and then stabilizes again. Okay, that would be a kind of natural cycle of this kind of platform. But now, if we destabilize them too fast, and most of them at the same time, let's say almost at the same time, then it would induce a lot of ice discharge at the same time. And this is what are our future projections about. Such disintegration occur because we say mostly of oceanic warming and because of the warm water intruding below those floating platform of Antarctica. So what happens? So you make the warm water penetrate into those below those ice shelf, okay? Then the ice shelf themselves are thinning, okay, because they are melting from below. Because they thin, at some point the ice flow coming from inland is not able to maintain the platform as a whole, so it disintegrates, and the ice sheet's response is to step back, but it means that most of the ice that was stable at a point is just lost to the ocean, and it has to retreat back just to get a new stable position, okay? So that's called a marine ice sheet instability, and this is, as the name says, an instability. As such, is hardly predictable. Okay, because it means that we have to determine the threshold on oceanic temperature from which then such disintegration might occur. Another kind of instabilities is what we call the marine ice cliff instability, okay, that also occur on the ice shelf and has the same effect. It's because it's due mostly on the surface melt of the surface melt, okay? If the temperature are warm enough to produce melting at the surface of ice shelf, the meltwater penetrates into the crevasse of those ice shelf. When the winter happens, it just freezes again and then enlarges the cracks and creates some hydrofracturing processes that make it very easy then to disintegrate if ocean warming below is particularly aggressive. So it also produces a huge discharge of ice into the ocean and a very large sea level rise, even larger than the marine ice sheet instability because it combines both. An important aspect of those instabilities is that they can trigger everywhere. However, if the ice sheet is resting on a bedrock that has a slope oriented toward the interior, okay, so in the sense of in the direction of the retreat then of the glaciers, of course it enhances the retreat because it helps the ice to retreat further into the inland and to lose more ice. So the configuration of the bedrock sloping inland, okay, toward the interior is highly important. That's a very important factor. But that's also one of the sector of Antarctica where we have most of the knowledge gaps, because it means that we have to see what is below the ice in Antarctica, and it seems easy to say, it's less easy to really observe. So we have few methods to really understand how is the bed in Antarctica, but in most sectors where we have those floating platforms, we are still lacking of data, and we are still unsure of how the configuration of the bed is in all those areas. So potentially, we are also a bit underestimating some of the ice shelf vulnerability. So now, one of the ice shelf in West Antarctica is the Thwaites Glacier. The Thwaites Glacier is a very good example of what's occurring to West Antarctica. Okay, most of the oceanic flows penetrate into the cavity, melt the ice shelf from below, and we have been seeing this ice shelf thinning over the 21st century, and we are seeing the first sign of retreat of grounding line. So that's a glacier that is potentially very, very sensitive and has the potential to drain a lot of ice mass into the ocean, leading to a few meters of sea level rise if it occurs. Okay, so that's one of the main glaciers that is under monitoring right now by the community because of the potential sea level rise it might cause. Now, if we have a look at the projections, okay, this is a timeline, okay, of the various scenarios that have been simulated by Rob De Conto a few years ago. I'm not looking at it for the rate of global mean sea level rise, but more the timing of the different sectors. So the acronym correspond to various sectors of Antarctica. What is important here is that this AZ acronym, okay, the second one, Okay, it represents this part of West Antarctica that is highly vulnerable to oceanic melting. And you can see that it's one of the first sector to trigger in case of oceanic warming that is very high in the RCP 8.5 scenario, which is the worst case scenario, okay, the warmest one, actually, the one we are almost following the track right now. Okay, so that's the second sector to trigger. The first one are the glaciers of the Antarctic Peninsula, but that's normal because they are located northwards, so they are subject to a warmer climate context, let's say. But the second sector to trigger is West Antarctica, and then a few glaciers of East Antarctica, and then again West Antarctica, and then a few glaciers of East Antarctica. But so West Antarctica is the first one that would be lost in case of we cross the threshold of oceanic warming. What is the timing of this such instability? So about 2 centuries, 5 centuries, okay? But the trigger is fast. As soon as we cross the threshold, which we are not sure about, we could have already crossed it or not, then it has anyway long-term consequences, because it's not that we disintegrate the entire West Antarctica in 10 years. It doesn't happen this way. Anyway, it just happens in 2 to 3 centuries in the simulations, okay? This sector of West Antarctica. It causes a multi-meter sea level rise, okay, in 2 to 3 centuries. So it means at least 1.5 meters by the end of the 21st century. So that's a lot. Because now if we think that we are already have been having 20 centimeters of the global mean sea level rise, and many areas that are low-lying countries like small Pacific islands or other very low-lying countries are already suffering from sea level rise. Imagine 1 meter more plus the high tides and storm surges. Oh, that's a very nice simulation done by my colleague here and PhD students. That shows you, in case of this worst case scenario, okay, 8.5, what happens to Antarctica if it disintegrates. Not sure it would. So have a look at this sector here that shows the brightest color. Basically, it shows you how the ice disintegrates in time. You see the dark blue color retreating back, because as soon as the destabilization occurs, the grounding line is retreating, and most of the light blue colors and bright colors means that the ice is thinning, floating, disintegrating, and lost to the ocean. So that's quite fast. I mean, we lose a lot of sector in a few amount of time, and that's the projection, that official projections done by this intercomparison project called ESMIP6, okay, which gather most of the ice sheet modelers of the community right now. So while a few years ago, I would say we were really unsure about this grounding line retreat and a very rapid ice discharge from those sectors, now we have been monitoring extensively from the ocean point of view, from the ice sheet point of view, and using different models to now understand much better than many things that we have been observing that we didn't understood now. We are able to interpret them and be a bit more sure that, okay, now we are running fast, we are running against time, we're lacking of time, and we will probably lose those sectors anyway. Another important aspect of the ice is that it's like the ocean; it absorbs the heat on a very long time scale. So as such, it also melts on a very long time scale. So even if we stop warming now, the warmth in the ocean will still continue to melt the ice shelf around Antarctica for a few centuries. So part of this process is unavoidable anyway. So this will happen no matter what we do. But this doesn't mean that we don't have to do anything. We have to mitigate as much as possible, because the more warmth the ocean absorbs, and of course the larger ice discharge we would have afterwards. So it's much better to maintain all the global warmth to 1.5 degrees and perhaps even less, as paleo data are suggesting. So we are very sure to limit the sea level rise, but we can't avoid it. So we have to adapt anyway. It also happened in the past. I mean, that's the last slide of this presentation, but I wanted to give this past perspective, because it's important to understand that what we're projecting is just not an invention. It's just not a science fiction movie. It's really happening. So this graph shows you the reconstruction of CO2 in the past up to when Antarctica started to glaciate, so 34 million years ago. At that moment, the CO2 concentration was 1,000 ppm in the atmosphere. Then it quickly dropped around 400. It stayed above 400 ppm for a while. and then after drop below the 400 and then 300 ppm, which is all what the ice core records are telling us about the last 2 million years of our Earth's climate history. And then in our 21st and 20 and 21st century, we have been rising the concentration again. And at the end, you can see the different scenarios of emission for the sectors in in East Antarctica, but we'll speak about this afternoon. It happens another period where CO2 was a bit lower than 500 ppm. Okay, same sectors collapsed. You can see that Antarctica is not the whole ice sheet that we know today. And we know it also happened when CO2 was below 300 ppm, and that's the most interesting part, because 300 ppm means that climate was cooler than today. It was about pre-industrial temperature and even a bit cooler. Okay, now, I mean, nevertheless, collapse happened because of some connection with the northern hemisphere and the southern hemisphere oceans, actually, that transport the heat from the pole to the equator and vice versa. Okay, some heat transfer can occur in case Greenland ice sheet melt very fast in the northern hemisphere. In this case, it slows down the thermal line circulation in the northern hemisphere, but it transfers all the heat to the southern hemisphere, so it amplifies the Antarctic melting in that case. So even if CO2 is very low, collapse can happen because we melt other ice sheets in the northern hemisphere. 300 ppm, it's very well below even the 1 degree target. 1.5 degree target would be to go back to 360 ppm. Okay, so if we want to really let's say secure a sea level rise that is about 1 meter, 2 meter, not more, we really need to stay below 1.5 degrees. I mean, so that's the paleo perspective. So because of that, we are quite sure that rising our CO2 in the atmosphere, or rising our carbon emission anyway in the future, will make a lot of Antarctic sector to collapse anyway, and West Antarctica first. I think that's it. So if you have questions. Oh yeah, okay.
With the rising temperature, are we seeing increase in rainfall in Antarctica like we are in Greenland?
Okay, so Antarctica is really located at the South Pole. Okay, so it's make it harder to see rainfall until a while. We start to see rainfall at the very end of the 21st century when temperatures are very high, close to Antarctica. Then, yes, some of the melt of Antarctica at the surface that will occur at the end of the 21st century because temperature during summer start to be above zero are largely compensated by the gain of snow and precipitation around Antarctica by the end of 21st century. But this will be short because as soon as we go up in temperature anyway, at some point the melting will be higher than the gain of, and precipitation will not help further. Yeah. For the question. Oh, sure.
Hi. My question, I was talking to Chen about this earlier, is I'm more familiar with the Arctic specifically. So I was kind of wondering what are the main differences you see between the Arctic and the Antarctic in terms of warming, just effects in general, since I'm more familiar with the Arctic and love learning about the Antarctic.
Okay, so we are talking about two different contexts. Okay, so Antarctica is an ice sheet that rests, it's a terrestrial ice, so rests on the continent that is very located south pole. The Arctic is an ocean that is covered by sea ice during winter and normally multi-year ice during summer. Okay, so the main difference is that, for example, in Arctic, what happens is that the ocean warming causes a lot of summer sea ice melts, okay? And it has started also to retract the multi-year ice component of the sea ice. And this one was a bit perennial from our time scale point of view, let's say. And when you remove the sea ice during the summer, the ocean surface is much darker than the sea ice surface, which is completely white. So the sea ice surface reflects 90% of solar radiations. So if you remove the white surface, what you see below is the ocean surface, which has a much darker surface. So it absorbs the heat instead of reflecting. So it's a positive feedback. You retract the sea ice and the ocean below absorbs more heat, so it's warming more, so you retract more sea ice, etc. So in the Arctic, the projections say by that mid-century, we lose completely the summer sea ice cover. Then it freezes again during the winter, but we lose the sea ice summer. So it means that it will warm and warm and warm and warm and warm. In the Antarctic, it's completely different because this is an ice sheet, 3 kilometers thick. And so it's vulnerable to ocean warming at the margin, as we say, because of this instability and the role of ice shelf in maintaining the flow inside the inland on the continent and thus regulating the ice discharge into the ocean. It takes a while for the ice sheet to really contribute very much to sea level change. That's why the two different scenarios by the end of the 21st century, it is different, not that much. But if you look on the long-term projection that's shown by IPCC, so by 2300, there you see the divergence between the scenarios. But the processes are different. The Arctic is warming so fast, much faster than Antarctica because of ocean warming and the changes in the reflectivity of the surface. While Antarctica still takes a while to really let's say have a real strong impact, because right now in the two scenarios it is projected that Antarctica have about 15 centimeter contribution by the end of 21st century. Then going beyond, because of this impact of thermal inertia of the ice, then the contribution starts to be higher because of instabilities behavior and very fast discharge on this time scale. So that's mainly the two differences of the region. Okay. But if you don't have any further questions, thank you very much. And see you soon. Come to this event this afternoon about East Antarctica. 1 p.m. Yeah, 1 p.m. sharp here.